Recording has started.
Well, let's take a look and see how you're doing on these so far. Number one here, there's just multiplication and division, and technically that all happens at the same time. But when we have the fraction bars are an enclosing symbol. So we need to do this division first. 10 to the 8th divided by 10 to the negative 5. Well, that's going to be 10 to the power of 8 minus a negative 5, which is a positive 13. Now I'm going to combine some steps here in one. The next would be to do that division. 10 to the negative 3 divided by 10 to the 7th. That's going to be 10 to the negative 3 minus 7, which is negative 10. So now I'm going to multiply those. 10 to the 13th times 10 to the negative 10. We add the powers when we multiply. 13 plus negative 10 is 3. So that is 10 to the third power. Over here, fraction bar says we have to do what's on top first. So 10 to the 5th times 10 to the 7th. We add the powers, that's 10 to the 12th. On bottom, first thing we have to do is this fraction bar. So the 10 to the negative 6th isn't going to change. 10 to the 5th divided by 10 to the 8th. 5 minus 8 is negative 3. Well, now we can continue on bottom. The 10 to the negative 6 times 10 to the negative 3. That's 10 to the negative 9. Then we divide. The 10 to the 12th divided by 10 to the negative 9. 12 minus a negative 9 is 21. That is 10 to the 21. And then to the power of a negative 3, remember when we do a power of a power, we multiply. So 21 times negative 3 is a negative 63. So number 3. First non-zero digit here is the 3. We have to move the decimal point to be after that. That's 1, 2, 3, 4, 5 spots. We make that 3.9 times 10 to the, it's either going to be 5 or negative 5. That is a small number, so it's a negative power of 10 place value. Here, the first non-zero digit is the 6, so we're going to put the decimal point after that, so it'll be 6.2. It started out here, so it went 1, 2, 3, 4, 5, 6, 7 places. That is a large number, so that is 10 to the positive 7. Any questions on those? Okay, so today then, we want to look more at this scientific notation. As you recall, when we add or subtract, must have the same name. Well, when we were looking at whole numbers, that name came down to the individual place value. If I have something like 4.7 times 10 to the 8th, the part of this that implies a place value is the 10 to the 8th. So when we are adding or subtracting numbers in scientific notation, they must have the same power of 10. Then, just like any other number, we combine the counts. Then we keep the same name. So let's take a look at an example here. Let's say we have 4.7 times 10 to the 8th. Now those parentheses are not an enclosing symbol in this case. Just like with the negatives, they're just there to separate it to show you that that is a single number. Plus 3.1 times 10 to the 8th. First thing we need to check, these do have the same name. They're both 10 to the 8th. Now we can combine the counts. 4.7 plus 3.1 is 7.8. And then we keep the same name, times 10 to the 8th. We might have something a little bit more difficult. 6.4 times 10 to the 12th plus 8.9 times 10 to the 12th. Well, these still have the same name. They're both 10 to the 12th. So we'll combine the counts. 6.4 plus 8.9 is 15.3 times, we keep the same name, 10 to the 12th. However, there's an issue here. Right now, there are 2 digits in front of the decimal point. Proper scientific notation only has 1 digit in front of the decimal point. So we have to move that decimal point over to make that 1.53. Now, things have to balance here. We moved the decimal point to make this number smaller. It went from 15.3 down to 1.53. By 1 decimal place, it got smaller. So we make the power of 10 larger by 1. That is 10 to the 13th. We might have 8.2 times 10 to the negative 9 plus 4.1 times 10 to the negative 9. Again, we have the same power of 10. They're both 10 to the 9th. So we can go ahead and add them. We'll combine the counts. 8.2 plus 4.1 is 12.3 times 10 to the negative 9. Once again, there's 2 digits from that decimal point. We're going to have to move the decimal point over to make that a 1.23. The number got smaller. It went from 12 down to 1.2. So the power has to get larger. But we have to be careful here. It's a negative power. Negative 9 plus 1 is a negative 8. That's 1.23 times 10 to the negative 8. We might have negative 3.5 times 10 to the 7th plus 6.1 times 10 to the 7th. So once again, we have the same power of 10. We'll go ahead and combine our counts. We have a negative 3.5 and a positive 6.1. Tells us we're going to have a positive answer, and it'll be the difference between 3.5 and 6.1. 6.1 minus 3.5 is 2.6, positive 2.6. It would keep the same name of 10 to the 7th. What if they don't have the same power of 10? What if I have something like 7.32 times 10 to the 14th plus 9.4 times 10 to the 13th? They have different powers of 10. They have different names. Well, I have to give them the same name. I have to change one of them. Usually what works best is to go to the higher power. So this one is the higher power, so that's just going to stay 7.32 times 10 to the 14th. This one has to become 10 to the 14th. Now it's kind of the reverse of what we did up here. The power got larger by 1, so the number has to get smaller by 1 decimal point. That becomes 0.94. Now we have the same name, the 10 to the 14th. So we can combine counts. 7.32 plus 0.94 is 8.26. And we have the same name, 10 to the 14th. When we subtract, we also must keep the same name. Have the same name and keep the same name. So we might have 7.3 times 10 to the 5th minus 4.1 times 10 to the 5th. You'll notice we have the same power of 10. We have the same name. So we will combine the counts. 7.3 minus 4.1 is 3.2. And we keep that same name, times 10 to the 5th. We might have 6.32 times 10 to the 12th minus 5.51 times 10 to the 12th. They have the same power of 10. They have the same name, so we're good there. So we'll combine count. 6.32 minus 5.51 is 0.81 times 10 to the 12th. Now, again, we have an issue here because it's not proper scientific notation. Proper scientific notation has exactly one digit in front of the decimal point, and it cannot be a 0. So I have to move this decimal point over to make that 8.1. Now this time I moved the decimal point to make the number larger. It went from 0.81 to 8.1. So my power has to become smaller. So 12 minus 1 is 11. So it is 8.1 times 10 to the 11th. We might have 5.39 times 10 to the negative 8 minus 4.92 times 10 to the negative 8. Once again, we have the same power of 10, so we have the same name. We're going to go ahead and combine count. So we'll subtract. 5.39 minus 4.92 is 0.47. Times, we keep the same name, 10 to the negative 8th. Now again, that's not proper scientific notation. We need to move the decimal point a spot. We're going to move it over to make that 4.7. This number got larger, so the power of 10 has to get smaller. This got larger by 1 decimal place, so the power gets smaller by 1. So negative 8 minus 1 is negative 9. So it's 4.7 times 10 to the negative 9. So you have to be very careful, especially with the negative powers, to make sure you adjust those powers accordingly when you have to move the decimal point. When we multiply or divide, remember we do not need the same name. With fractions, this meant we didn't need this common denominator. With decimals, we didn't have to line up decimal points. Scientific notation, we do not need the same power of 10. We're going to combine our counts. Then we're going to also combine names, which means we're going to have to combine our powers of 10. So we might have 2.3 times 10 to the 8th. That looked like a 3. Times 1.8 times 10 to the 13th. It does not matter that those are different powers of 10s, because when we multiply, we do not need the same name. So 2.3 times 1.8, 4.14. Times, we're going to also combine the names. 10 to the 8th times 10 to the 13th. They have the same base, so it's going to be 10 to the power of, we're multiplying, so we add the powers. 8 plus 13 is 21. 4.14 times 10 to the 21st. So we might have something like 6.3 times 10 to the 12th times 4.1 times 10 to the 6th. Again, we don't need the same name, so we don't worry about the powers of 10. We're going to combine the count. 6.3 times 4.1, 25.83. Then we're going to multiply the names, combine the names. 10 to the 12th times 10 to the 6th, that's 10 to the 12 plus 6 is 18. Now, once again, this is not proper scientific notation. I have 2 digits in front of the decimal point. I need to move it over. So that becomes 2.583. This number got smaller by 1 decimal place. My power of 10 has to get larger by 1. 18 plus 1 is 19. So it's 2.583 times 10 to the 19th. Let's see here. Let's do something like 4.9 times 10 to the negative 7th times 7.2 times 10 to the negative 11th. So again, we don't care that we have different names. We're going to combine our counts. 4.9 times 7.2, 35.28. Then we also combine the names. 10 to the negative 7th times 10 to the negative 11th is 10 to the, we're multiplying, so we add powers. Negative 7 plus negative 11 is negative 18. And again, we have to move that decimal point over. Make that 3.528. The number got smaller by a decimal place, so the power here gets larger. Negative 18 plus 1 is a negative 17. 3.528 times 10 to the negative 17th. Let's do negative 6.3 times 10 to the 5th times 2.4 times 10 to the negative 9th. So we're going to combine counts here. Negative 6.3 times 2.4. Giving us a negative 15.12. Times, we combine our powers are 10, combine our names. 10 to the 5th times 10 to the negative 9th is 10 to the 5 plus negative 9 is negative 4. Now we still have to move this decimal point one spot. That's going to become a negative 1.512. So again, this number went from 15 down to 1.5. It got smaller, so my power of 10 gets larger. Negative 4 plus 1 is negative 3. So note that this negative up front here does not change the power of 10 at all. It doesn't change how we move our decimal point at all. Let's look at division. We might have 5.76 times 10 to the 12th divided by 4.8 times 10 to the 5th. We combine our counts. 5.76 divided by 4.8 is 1.2. We also combine our names. 10 to the 12th divided by 10 to the 5th. When we divide, we subtract powers. 12 minus 5 is 7. We might have 1.728 times 10 to the negative 9th divided by 1.2 times 10 to the 4th. Again, we combine our counts. 1.728 divided by 1.2 is 1.44. Times, we combine our names. 10 to the negative 9th divided by 10 to the 4th. Well, that's negative 9 minus 4 is a negative 13. We can run into things like this. 3.24 times 10 to the 3rd divided by 3.6 times 10 to the 12th. So we divide 3.24 divided by 3.6 is 0.9. We also combine the names. 10 to the 3rd divided by 10 to the 12th. Well, we subtract powers when we divide. 3 minus 12 is a negative 9. Now, this is improper scientific notation again. there's only the 0 in front of the decimal point. We have to have one non-zero digit in front of the decimal point. So I'm going to move it over to make this 9. The number got larger, so the power gets smaller. So negative 9 minus 1 is a negative 10. So that is 9 times 10 to the negative 10th. We can do things like 2.5 times 10 to the 7th squared. Just like with any other number, we square the count, but then we also square the name. 2.5 squared is 2.5 times 2.5. That's 6.25. 10 to the 7th squared. Well, when we take a power to another power, we multiply them. 7 times 2 is 14. That's 6.25 times 10 to the 14th. We might have 1.2 times 10 to the negative 9th to the third power. Well, we do 1.2 to the third power is 1.728. And then we do the power of 10, 10 to the negative 9th to the power of 3. Negative 9 times 3 is a negative 27. So 1.728 times 10 to the negative 27. Let's do something like this. 6.4 times 10 to the 5th to the power of 4. So we have to do 6.4 to the power of 4, which is 1,677.7216. Then we do the 10 to the 5th to the power of 4. 5 times 4 is 20, so it's 10 to the 20th. Now here we're going to have to move the decimal quite a ways. We have 4 digits in front of the decimal point. We want 1. We got to move it all the way over to there. So we have to move it 1, 2, 3 spots. We moved the decimal point 3 spots, making the number smaller. We went from 1,600 down to 1.6. So we have to make our power of 10 larger by 3, because we got smaller by 3 decimal places. So 20 plus 3 is 23. If I want to do a square root of 6.76 times 10 to the 18th. Square root of 6.76 is going to be 2.6. The square root of 10 to the 18th. Remember, what that's asking is, what number squared equals 10 to the 18th? Well, when we square something, we multiply the power by 2. So going backwards, square rooting it, we're going to divide the power by 2. 18 divided by 2 is 9. So that's 10 to the 9th. 10 to the 9th squared would give us 10 to the 18th. So the square root of 6.76 times 10 to the 18th is 2.6 times 10 to the 9th. This means third root, of course, of 1.728 times 10 to the negative 12th. Well, we do the third root. The third root of 1.728 is 1.2. And just like up here, we divided the power by 2 to take the square root. To do a third root, we're going to divide the power by 3. Negative 12 divided by 3 is a negative 4. So 1.2 times 10 to the negative 4. So that's all of our operations that we want to be able to do with scientific notation. Now there's something else out there called engineering notation that is used in electronics and other spaces. Engineering notation is similar to scientific notation, only instead of just one digit in front of the decimal point, you can have 1, 2, or 3 digits in front of the decimal point. And the power of 10 has to be a multiple of 3. Remember, we talked about multiples briefly when we did factoring at the end of Unit 1. Multiples of 3 are 3, 6, 9, 12, 15. But they're also 0, -3, -6, -9, going backwards. So proper scientific notation, or proper engineering notation for something like 84 million. We still move the decimal point just like we do with scientific notation, but for engineering notation, we have to go 3 decimal places at a time. So starting here, we go 1, 2, 3. Well, we can go 3 more, so it's 4, 5, 6. We cannot go any more, so that's 84. That's where the decimal point ended up, times 10 to the 6th. We might have 280,000 if I want to convert that into engineering notation. Decimal point starts here. It goes 1, 2, 3. I cannot go 3 more, so that's 280 times 10 to the 3rd. Something like 0.00943. Take our decimal point, we go 1, 2, 3. Well, there's already digits. When we're going in this direction, we just go 3 spots at a time until there's at least 1 digit, non-zero, in front of the decimal point. We're going to stop there. That's 9.43 times 10 to the -3rd. But it can be a little weird when we have a number like this, 0.00072. We move our decimal point 1, 2, 3, and it looks like we cannot go 3 more, but we have to, because right now there's nothing other than zeros in front of the decimal point. So we have to go 4, 5, 6, adding a 0 there. Get that as 720 times 10 to the -6. So the big question is, why? Why do we have this engineering notation? Scientific notation kind of made sense. It's the place values of our leading digit. Why is engineering notation even a thing? Well, because if you get into electronics, you have volts, amps, ohms, so on. Well, skipping up, you have kilovolts, kiloamps, kiloohms. If we consider the original unit to be 1 or 10 to the 0, kilo is 10 to the 3rd. We keep going up, we've got megaamps, megavolts, megaohms, that's 10 to the 6th. A megaamp is huge, by the way. Kiloamp is huge. Going smaller, we go down to milli. A millivolt is 10 to the -3rd volts. Keep going, we have micro. Microvolt is 10 to the -6th volts. So if I have an operation like volt equals current times resistance. So let's say I have 24 milliamps times 1.2 kilo ohms. Well, I can change this in engineering notation. 24 milliamps, milli is 10 to the -3rd. Times 1.2 kiloamps, kilo is 10 to the +3rd ohms. So now I multiply 24 times 2.4, going to be 28.8. Not, no, 24 times 1.2. So we do times, not divided, is 28.8. And then 10 to the -3rd times 10 to the +3rd. Well, -3 plus +3 is 0. That's 10 to the 0. An amp times an ohm is a volt, so that's just 28.8 volts. Now, in automotive class, when you guys do DC electric, Rick usually tells you convert it to 0.024 and 1,200 and multiply them out, which that works great. Especially when you're first starting out, that does probably make a lot fewer mistakes. But you can work with the units directly. We might have, for power, we know that power equals current times voltage. So we might have a current of 35 milliamps and a voltage of 2.5 mega volts. So we have 35 milliamps times 2.5 megavolts. We do 35 times 2.5, which is 87.5. Now it's okay to have two digits because it's engineering notation. We can have 1, 2, or 3 non-zero digits in front of our decimal point. For milli, remember this is 35 times 10 to the negative 3 amps. Mega, that's 2.5 times 10 to the 6th volts. So we have 10 to the negative 3 times 10 to the positive 6, which is 10 to the positive 3, 10 to the third. An amp times a volt is a watt. 10 to the third is kilo. This is 87.5. 10 to the positive 3 becomes kilowatts. We'll let you off the hook with your homework here. In the book, page 130. Exercise 2.6, it is 59 through 81, the odd. And then on page 133, exercise 2.7, 1 through 23, the odd. So working with our operations with scientific notation and then some basic engineering notation. So you guys can have